experiment semiconductor laser diode or laser. So here also we will use the, it is also simple p-n junction diode only. Once these electrons holes will recombine, it will emit the photon. This simple p-n junction diode, and it will, when electron hole recombine, it emits the photons. It emits the photons. So that is what laser beam means. Okay. So here also, if photon emitting means, you always remember, here we are using direct band gap semiconductor. Okay, direct band gap semiconductors. Okay, suppose if you want to emit phonons, then use the indirect band gap semiconductor. Okay, these two things are very important. So before starting the laser experiment or any preparation or fabricating the laser or LED, so our aim is to emit the photons. To emit photon, which band gap material we have to choose means, here we have to choose direct band gap materials. So here semiconductor laser diode means, or semiconductor laser means, it's a simple p-n junction diode. So when electron hole recombine, it emits the photons. Okay, this will happen in direct band gap semiconductor. Okay, so that's it. Yeah. So remaining these photons we will amplify the using cavity there, but here also we will create similar type of cavity, optical resonator. Then we will amplify the light. Okay, I will explain that one. So here two type of semiconductor lasers are there. One is homojunction laser, homojunction, and second one is homojunction laser, and second one is heterojunction laser. Okay, heterojunction laser. So what is mean by homojunction? Please tell me what is mean by homojunction. Please
It
answer
is
this.
similar.
Yeah, similar. So here laser diode means p-n junction diode. Here also, if you make the junction using same band gap material, that is homojunction laser. Okay, same band gap material. Homojunction means if you form the p-n junction by same band gap material. If you form the p-n junction by same band gap material or equal band gap material. And yeah, materials are material. Okay, whatever it is. So that is what you form the homojunction uh, diode. Here, if you form the p-n junction diode, p-n junction diode by different band gap materials. Okay, different band gap materials. So that is what difference between homojunction and heterojunction. So what are the advantages of homojunction, or what are the disadvantages of homojunction laser? We will discuss. Why after homojunction, why we are reading heterojunction, that is also we will discuss. Okay. So homojunction means, suppose if you take gallium arsenide here, gallium arsenide, GaAs, gallium arsenide. This is compound semiconductor and direct band gap semiconductor. The band gap is, what is the band gap? Do you know? 1.4 electron volts, 1.44 or 1.5 electron volts. Okay. So here we will take p type and n type, same material. Okay, here we will make the same p type and n type, then it will form a homojunction laser. So first what we will do, so if you make the junction or if you form the junction, suppose it is n type gallium arsenide, and on top of that we will make the p type gallium arsenide. Okay, p type gallium arsenide. Okay, this is p-n junction diode, right? Isn't it? Just here p type material is there, n type material is there, then it is forming p-n junction. Okay, is it right?
Yes, sir.
Yeah. Okay, after that we are making one more layer. This is metal layer. Okay, metal, some silver or aluminum, whatever. Okay, this is some metal layer. You can write metal here. On top of that also we'll take a metal layers, metal contacts. Okay, so this is just like a p-n junction diode. So here what happens, when you give some energy to the semiconductor or biasing voltage, okay, biasing voltage to this semiconductor, these electrons and holes will recombine in the depletion region. Once they recombine, it emits the photons, right? So here this there is a chance of emitting photon this side and along front side and back side, right? Along the junction. So what we will do, we want only one direction, right? So what we'll do, this surface will cleave this one. Okay, we'll cleave this one, cleaving. Okay, cleaving. Okay, we'll cleave this surface. That means photons will not come this side. Only they will move one direction only. Okay, they will move along one direction only. This is the simple construction of the laser diode. Same thing we will do in our laser also. Whatever you have done experiment, similar way also. First they will take the same one material, suppose N type gallium arsenide. On top of them they will fabricate or deposit P type gallium arsenide, and front and back to apply some voltage. They will take the metal contacts. Okay. After you apply some biasing voltage here, electrons will go to the excited state and will create the population inversion. Once they recombine, we will get the laser beam. Okay, there is a chance of going back side and front side. So we will block this surface. Okay, we will block this surface and only it will move the front side only. This is what a cavity or resonator you can say. So here, see things like. To produce laser beam, okay, to produce laser beam, what we have to do, first you need the material. Okay, that is we are taking gallium arsenide material, and that is active medium. And second thing, you have to create population inversion, isn't it? So how you will create population inversion here? Suppose it is a semiconductor, this is conduction band and this is valence band. So here we will say at 0 Kelvin, these all are bound electrons, right? Bound electrons, these are not free. Okay, once you give this some temperature to this semiconductor or some voltage to this semiconductor, what happens? What happens when you
They
give some?
jump higher.
Yeah, they break electron break the these bonds, covalent bonds, and they will become free in the conduction band. These are free electrons and here free holes. Okay, so compared to here electrons, suppose this is N2 or N1, or you can say E2 and E1. So we will take in case of electron. Okay, so once you give some biasing voltage or some temperature, we have achieved number of electrons in the higher energy state greater than the lower energy state, right? So N2 greater than N1. So that means what? We have achieved population inversion. Number of electrons are higher in the conduction band compared to valence band. In case of if you take holes, so number of holes in lower energy state is greater than the higher energy state. Correspond to electron, this is the population inversion. Correspond to holes, this is the population inversion. Because holes always will be available in the ground state, means lower energy state, that is valence band. Okay, so if you compare holes in the conduction band and valence band, holes are higher in the valence band, isn't it? And if you compare electrons, electrons are higher in the conduction band compared to valence band. Is it right?
Yes,
Okay.
sir.
Yeah, this way we'll create the population inversion. After that, these electrons will jump here and recombine. Now we'll see that how this will recombine using some band bending diagram. Okay, that we'll see. Okay, just a second. I will draw and you will be clear. Okay, already we have many times we have drawn the band bending diagram. Okay. So same thing you draw it. Just here we have a Fermi level, and here we are taking P and N. Okay, so just like same thing. Okay, sorry, just a second. So P type is like this, and N type like this. Okay, so now you join this one, and so here also energy gap is same, that is 1.4 electron volts. Here also energy gap is same band gap we have taken. This is 1.4 electron. Here also gallium arsenide, p-type gallium arsenide. Here n-type gallium arsenide. Okay, that is we have taken. So here we have a free electrons, right? In the conduction band, free electrons. Here we have a free holes. Okay, so this is the depletion region. This is the depletion region, right? Up to now, is it okay?
Yes, sir.
Yeah, here we have a free electrons, here we have a free holes. Now this is once you apply some biasing voltage, we are getting the population inversion. This is already we have discussed. Okay, after actually we are not at room temperature, right? So we are at room temperature, right? If you give more voltage also, this more number of electrons will be created and more number of holes will be created. So now here also, suppose you want to emit the photons. So how you will emit the photons? When electron hole recombine. Okay, when this electron hole recombine, under forward bias or under reverse bias? Which one is required here, forward or reverse?
Forward bias.
Yeah, forward bias. When you give forward bias, holes will move towards the junction or towards the depletion region, and this is positive and this is negative. Okay, and electrons also move towards the junction, right? So now these electrons will jump into the valence band and they will recombine. Once they recombine with these holes, this will emit the photons. This will emit the photons, right? These photons we are using, one side we are blocking, one side only we are sending. So how we are getting here, when we discuss it there, in lasers we have discussed spontaneous emission process and stimulated emission process, right? So how these are taking place here, spontaneous and stimulated emission process. Here we are not seeing any spontaneous emission or stimulated emission. So why we are not observing this one here? And when you studied helium and laser, gas laser, always we are saying spontaneous emission, photons are emitting. These photons will trigger the stimulated emission, right? And we will get the two photons here. So in spontaneous photon, so suppose there is excited state, they will immediately jump to the lower energy state, emits the photons. This is spontaneous photons. After these spontaneous photons, if suppose here atoms are there, again this will trigger these remaining atoms, and now these atoms comes to the ground state. This is here stimulated emission process. Okay, so to start the stimulated emission process, you need some external photons. That photons we are getting from the spontaneous emission process, right? That is what we have discussed in helium ion and gas lasers. To start the stimulated emission process, to trigger the stimulated emission process, we are utilizing the photons which are emitted in spontaneous emission. Okay. So, but here we are not seeing, when you electrons are jumping from conduction band to valence band, they are recombining and emitting photon. So, where this spontaneous emitting, where the stimulated is emitting? Just tell me here. Do you understand question? Where we are seeing the spontaneous and stimulated emission, we are saying just electron jumps valence band and emits the photons. But where are these spontaneous and stimulated emission process? Okay, see here very carefully. So when I explain second unit, suppose here valence band means, okay, here conduction band means what I said is a number of states. Okay, here number of states. Here also number of states, like this, right? Here also when you discuss the band bending here, okay, this time this drawing again like this. So here also there are number of states are available. Okay, number of states available. So just like draw this diagram. So like that, this is the depletion region, and this is the uh, Fermi level. You can write like this. Okay, this is Fermi level. Okay, now here we have a free holes here. Okay, right? Here also we have free holes. Let's take in this state we have free holes. In this state we have free holes. In this state we have free holes. Similarly, electrons also, in this state we have electrons, right? In this state we have electrons. Okay, in this state we have electrons, right? So here let's take here the conduction band, one, two, three states are there. Okay, the third state having lifetime higher or layer compared to T3, T1, T2, T1. Which one is having higher energy state? Higher energy in this conduction band?
T3.
Yeah, third level is highest energy. That means lifetime of this third level is lesser, right?
Low.
Low. Tau 3 greater less than uh, tau 2 less than tau 1. So when the third level energy is very high but lifetime is very less, so this will jump into the first in the conduction band. They will recombine with holes. So here they immediately come to the ground state and the valence band and jump into here, and they will recombine. Once they recombine here, it will emit this one photons. This is spontaneously. But in the first energy level, the lifetime is higher. So here electrons will stay for some time. Okay, these photons will trigger remaining electrons in the lower energy states. Once these photons, external photons are forcefully send these electrons to the ground state. Okay, then they will jump to the valence band and stimulated emission process takes place. Okay, like that here stimulated photons will emit. Okay, right? So here what we are doing simply, so here many energy levels in the conduction band, in the ground state also, this is valence band, this is conduction band. So first one, 3, 2, 1. Okay. So in the third level, electron jumping to the conduct valence band and making spontaneous emission. Here photons are emitting. So these photons triggering remaining electrons in the lower energy states. Okay, this will triggering these electrons, and these electrons jumping into the valence band, and they are recombining with holes. Here stimulated photons are emitting. Stimulated photons. Okay, this is what spontaneous emission process, stimulated emission process. That's why we'll say it's a band, means it's not a band, just only one state. Here many states are there, many states are there. So when electrons excited to higher energy level, they immediately come to the ground state because lifetime is very less. Okay, once they come to the lower energy state or valence band, they emit the spontaneous photons. These photons will trigger remaining electrons in the lower energy states. Okay, or these photons, whatever photons emitted in the spontaneous emission, will start the stimulated emission process. Okay, by sending electrons to ground state. Okay, then we'll get the stimulated photons. Okay, is it clear to you everyone this concept?
Yes, sir.
So thing is here only band means many states are there. First higher energy state, less lifetime. Okay, they will come first downside, and here they will recombine with holes and emits the photon. Emits the photon. This is spontaneous photons. So in the lower energy state, electrons also there, but this lifetime is higher. Okay, so electrons are staying for some time. These spontaneous photons will trigger these electrons. Then this electron come to the ground state and recombine with holes. In this case, stimulated emission process takes place and stimulated photons will emit. Okay, that is why here this that is the process happen in semiconductor lasers. Okay, now this is the thing. We will get the laser beam. After that, one surface will cleaving this one, and will sorry, just a minute. This is gone. Just a second. So this way, when you give some biasing voltage, electron hole will recombine. Okay, by jumping conduction band to valence band, and first, sorry, I'm not sure. Okay, this way holes will electrons will jump from conduction band to valence band in the depletion region, and this will recombine, this electron hole recombine and emits the photons. Okay, this way we will get the laser beam in semiconductor laser. Okay, now if you see this one, semiconductor laser, try this one again. So just like this. So here, so there is a chance of this holes also, there is a chance of this holes also diffusing to the end side. Okay, this is P and end side. So these holes may diffuse here and electrons may diffuse here because there is a less band potential height or potential barrier. Okay, there is a less potential barrier height. If we give more biasing voltage, this electron, there is a chance of enter into electrons should there is a chance of electron should enter into p side. Okay, if this electron enter in p side, instead of recombining here, instead of recombining here, if they enter in p side, these holes and electron will recombine. Okay, instead of holes recombining in the depletion region, if they enter into n side, these holes and electrons will recombine. Okay, once they recombine, there is no useful here. Okay, this light again absorb in the bulk medium. Okay, once this recombine, here also photon sends, but this is not useful. This again absorb in the bulk medium, so that is not useful. So always electron hole should be recombined in the depletion region. Then only these photons will emit. These photons only useful. So here active area is depletion region. In case of solar cells, or here also depletion region is same thing. Okay. So here main drawbacks are, so refract is a band gap is same means material is same means refractive index also same, isn't it? Refractive index of p side and the refractive index of n side also same, right? Isn't it?
Yes, sir.
So
Yes, sir.
first drawback is electrons may diffuse into p side because of less potential barrier. There is a chance of diffusing into p side. Similarly, holes may diffuse into n side. Okay, in the bulk region because of the less potential barrier. Okay, less potential barrier. So because of this one, electron hole recombine in the bulk region. If they recombine in bulk region, there is no useful. Okay. And second thing, same refractive index. This year, these are having same refractive index. That is also one drawback. Sorry, same refractive index. And third one is active area is not defined, well defined. Active area is not well defined. Well defined. Defined. These are the some drawbacks in homojunction layer. Okay, see here. Just I am draw again. This again created and I will draw. Okay. So here this is the Fermi level. This is the interface, and just a second please. So this is the depletion region. That is what active area means. This is the active area. So it is about distance is about 2 micrometer. This distance is 2 micrometer, generally order of 2 micrometer. So if you, this is the energy gap. If you plot the refractive index of the material, here also it's like a same. The height is very less. This is refractive index profile. Just I am writing n. Refractive. This is also 2 micrometer. Here this the difference is very less between P and N semiconductor because of the doping slightly change, but that is very small because of the same refractive index and less potential barrier. Holes here, holes will diffuse into P inside and they will recombine with electrons. Okay, here electron hole recombine, that will be emit photon, but this is not useful for laser beam. Okay, and here one more thing, the active area is not well defined like this. It is a spread out area. Okay, that means here we will get the maximum output when the at the interface, when electron and hole will recombine, we'll get the photons, right? So in the depletion region, we'll get the maximum output. Okay, if you move from center of the depletion region to other side, both side, the recombinations will reduce. Okay, recombination will reduce. That means output laser power will decrease. Output laser power will decrease. Only the active area is this is one, right? So this is not whatever here photons are. This area is not useful. This area is not useful, and because of this same refractive index, same material, we are unable to define exact active area. So this whatever this area is just useless area. Okay, that means here photons are emitting. These are we are not utilizing. So only photons, suppose same thing, if you define like this, okay, active area is like this, then that means here output power is more, here output power is less, because here well defined, this is well defined region, this is well defined region, here some loss is there, this is all, this part is there, no, beyond this depletion region this is loss, this loss in our laser output. Okay, so this loss should be decreased. Okay, these are the some drawbacks, or if you draw refractive index active area profile, these are the some drawbacks. Okay, to overcome this drawback, we are going to heterojunction layer. So heterojunction semiconductor, there band gap of materials, p side material is different and n side material is different, then we can reduce the recombination losses, and in the recombination losses in the bulk region. Okay, we can improve the uh, recombinations, or improve the recombinations or photons in the depletion region. That means we can improve the laser output using heterojunction. Okay, so drawbacks here, in homojunction, active area is not well defined and same refractive index, and there is a output also very less. Output is less. Output laser power is less, and there is a chance of electrons will enter in P region, P of the bulk region, and recombine electrons and holes. That is utilized in the same material only. That is not useful for the laser beam, producing the laser beam. Similarly, in case of holes also happens. Okay. This is the semiconductor homojunction laser. Is it clear to you guys?
Yes, sir.
Any doubts here? Any understanding or not understanding? Any doubt? Please tell listening or not.
No doubt.
So if you don't listen, I cannot help. Okay. In the exams also, if you don't listen, you cannot write. If you listen classes, I'm telling you, you can directly write the exam. You will pass. Okay. If you don't listen, you have to read very hard. Yeah. Because you don't know what is the terminology, what is the process, how things are happening. You cannot know. So then you cannot write also exam like this. So here simply what we are doing. So just I am repeating here. So by giving some biasing energy, we can create the population inversion. Number of electrons are higher compared to number of electrons in the conduction band. Okay, valence band conduction. First we are giving some biasing voltage. Okay, voltage. Okay, biasing voltage, and we are creating population inversion. Number of holes, electrons is higher than the holes. Okay, conduction band, electrons are higher compared to valence band. Okay, so this way we are creating population inversion, and whatever electrons, when electron recombine with holes, this will emit the photons, spontaneous photons. This photon again trigger the remaining electrons to come down, and this will again recombine. So first we will give the biasing voltage, and electron hole will move towards the interface or junction, and there it will recombine. When electron directly come to the excited state to ground state, they will recombine and emit the spontaneous photon. These photons trigger remaining electrons, okay, to come to the valence band and to recombine. Okay, once they recombine, we will emit the photons. So like this way photons will emit. One side of the laser junction will cleaving, will block the surface, and only other front surface only will get the laser beam. Okay, this way we will produce. And one more important point is here, if you plot the output power and this current, okay, injection current, this is injection current, injection current. Okay, this is I, and this is power, laser output power. Okay, up to certain voltage there is no power, after that it will start. Okay, like this we'll see the laser power. Okay, output power versus injection current. The circuit diagram is, you have already drawn this one. You can draw it here. Laser diode, there is a resistor, and here you have a diode. Okay, laser diode, and this will emit the photons. That's it. This is the circuit diagram. In circuit diagram already you have done that. So this is circuit diagram, simple circuit diagram. This is power versus injection current, or you can write current versus voltage also. If you, in the lab we have done this one, right? Current versus voltage, current versus voltage. If you apply voltage, sorry, I will try again. If you apply some voltage up to certain voltage, there is no current. After that, start increasing the current, right? This is the what you have done in the experiment. Okay, what you have done in the lab. So up to here, there is no power, means there is no recombination of electron holes. Okay, there is no recombination means no photons will emit. Okay, so after that, this is the IV curve, and one more drawback is we cannot operate this homojunction laser continuously, because if you draw this, if you write this one, I is equal to I0 exponential T by T0. Here T is the time, sorry, T is the temperature. Okay, it will depends on temperature. If you increase the temperature, the diode will heat up and it will not produce the power. Okay, power will reduce, it will heat up and reduce the output power, or performance will decrease. So this laser, homojunction laser, cannot run continuously. Okay, that is also one more drawback. To overcome this drawback, we have studied, we will go to the heterojunction laser. Okay, that we will discuss tomorrow. Okay, any doubt up here? So what you will write first, if they ask in the exam, first you write the definition. What is homojunction? Okay, what is the homojunction? Write how you are getting population inversion or lasing action. This population inversion and lasing action you write. These two terms. Okay, lasing action. How you get the lasing action, and after that, how recombination photons are emitting, or how photons are emitting, and you write construction. Okay, construction also we have to write, and this band diagram, band bending diagram, band bending diagram, and this IV curve, and power versus I curve, and next circuit diagram, and uh, advantages and drawbacks. This you have to write. Okay, this you have to write, depends on how many marks question is. Okay, it comes how many marks, depends on, you have to write this. Okay, tomorrow we will see the heterojunction laser. Okay, is it clear today class? Any doubt? So okay, I don't know.